Okay, here we have an example of a curve sketching question involving a rational function. And a rational function is simply f of x equals 2x over x plus 3 all squared. And we're given, and will always be given, the first and second derivative. Okay, and we're going to use those to find, in the first case here, extreme points, relative max, relative min. And with the second derivative, we're going to find points of concavity, inflection points. And you're asked to label all important features. So really for us, it's extrema, inflection points, intercepts as before, and with rational functions, we're going to have to find asymptotes. Okay, so those are the four main features that we'll look at. Get rid of this. So the first thing I do is I'm going to find extrema. So I set the first derivative equals 0 and solve for x. So this term here equals 0. You look at the numerator, 6 minus 2x equals 0, x equals 3. And you notice that negative 3 right here would make this thing undefined. So plus and minus 3 are critical numbers. Now, negative 3 cannot be a relative max or relative min. We know it's the intercept. So we'll put it here anyway, and we'll test the interval to see with increasing or decreasing. But again, while there's a critical number, it cannot be a high point or low point on the graph. So again, as before, you take a number in each of these intervals, you test and see what the sign is. And you're not required to list that number. Essentially, you would plug it in, is it positive or is it negative? And if it's negative, like it is here, it's decreasing right here. And between negative 3 and 0, at 3, for example, if I take 0, and if I plug 0 back into here, it's increasing. So, and I actually stated it right here. I stated the intervals where it was decreasing, which is negative infinity to negative 3, which is this one right here. And it's decreasing 3 infinity, which is this one right here. And between negative 3 and 3, it's increasing, so I actually stated that right here. Get a little messy, clean up a tiny bit. So again, sometimes you're asked to state those intervals, sometimes you're not. I just put them in. The fact is, we look at it and we see that it changes from positive to negative here, which means that we have an inflection point. So it's increasing and it hits 3 and it starts to decrease. So at this point right here, at the point x equals 3, we'll have a maximum value. It's increasing, then it's decreasing. So to find the y value, you plug 3 back into the original equation. Again, not the derivative. So you actually plug 3 back into here, and you get 1/6. So at the point 3 comma 1 over 6, we have a relative maximum value. And that's it. Okay. Again, sometimes you're asked to state the intervals where it's increasing and decreasing. If you're not, you don't need to do it. But you can get it from the graph. Okay, next thing we're going to look at is the inflection points. Where's the concavity change, if at all? And for that, we're going to use the second derivative, which is this here. So let this term equal 0, 4x minus 24 equals 0. So again, inflection points, second derivative equals 0, 4x minus 24 equals 0, x equals 6. So that's the possible point of concavity change, inflection point. And as before, 3 makes it undefined, but we know, negative 3, sorry, but we know that's a vertical asymptote. So it cannot be a point of concavity or inflection point. But we will test the interval to see if it's concave up or concave down. So again, you take a number in this interval right here, you test it, see if it's positive or negative, plug it into the second derivative. Take a number here, plug it in the second derivative, see if it's positive or negative. In both cases, these are negative, so it's concave down in each of these cases. And then take a number greater than 6, plug it into the second derivative, see what the sign is, it's positive, so it's concave up. So before we look at inflection point itself, sometimes you're asked on what intervals is it concave down or concave up. And you notice that from 6 to minus infinity, from negative 3 to minus infinity, it's concave down. From negative 3 to 6, it's concave down. And it's concave up on 6 to plus infinity. So here it's concave up. So again, it looks a little messy. Or you can simply state that it's concave down from 6 to minus infinity. Okay, so once we do that, you notice a change here from positive to negative. So that means we got an inflection point. Okay, and again, to find the y value, it's going to be 6, comma, and we plug it back into the original equation, f of 6, and we get 4 over 24, so 27. Sorry. So that means that there's an inflection point at that point here. Now again, we don't draw this to scale by any means. We simply sketch the curve. So I'll erase this so you can see it a bit better. So those are 2 points we have now. We have a relative maximum point, we have inflection point, and now we're going to look at finding asymptotes. And this is something that we covered way back when we did limits early in the term. And to find a horizontal asymptote, we simply find limit as x approaches plus or minus infinity, and we divide it by the highest power of x. And since that the degree of the numerator is less than the denominator, we're going to get 0. Okay, and if we want to work it out, you certainly can. Divide everything by x squared, and you have limit as x approaches infinity of 2 over x, and you get 0 over 1, which is 0. So we know that we have a horizontal asymptote at y equals 0, which is simply the x-axis. Just be a little careful you don't write down, which many of you have done, HA equals 0. I know what you mean, but this is not a logical mathematical statement, so be a little careful with that. So y equals 0 is your horizontal asymptote, which again is simply the x-axis. And by inspection, we look at the original function again, which is here. When x equals minus 3, this is undefined. So this by inspection, we can tell that x equals negative 3 is a vertical asymptote. And we already stated it earlier, but we want to verify it now. So we take the limit as we approach from the left-hand side and as we approach from the right-hand side. So you plug in negative 3, and I'll get, in both cases, I'll get negative 6. Right? And it'll be 0 behaving in a positive fashion. So plus over minus will give you negative infinity and negative infinity. So we've actually verified that it is a vertical asymptote at negative 3. And in both cases, it's approaching minus infinity. Okay, and finally, look at intercepts. X equals 0, you get y equals 0, so that's pretty easy to see. Okay, now I will sketch this. This sketch here is actually taken from a graphing utility from the web. It doesn't need to be this detailed by any means. I'll draw a freehand sketch below. But what do we know? Well, we know that x equals negative 3. Negative 3. Right. Negative 3 is a vertical asymptote. I'll just erase this right here. We know that y equals 0 is your horizontal asymptote. We have an intercept at 0, 0. We have a maximum point at 3, 1/6, and we have an inflection point here. Now again, it's very hard to see here, so I'll try to draw a freehand below to give you an idea. The key here is to simply sketch. So I can start off by drawing your x and y intercepts, and you label things. So we know that y equals 0 is your horizontal asymptote, and about here, x equals negative 3 is your vertical asymptote, and we have an intercept right here at 0, 0, and roughly about here we've got 3, 1/6 is a maximum point, and over here we've got 6, 4 over 27, which is an inflection point. And now it's simply a matter of connecting the dots. And if you recall from our graph, both from in concavity, for x less than 3, if you go back here, it's concave down. And we also verified it by looking at this graph, it approaches negative infinity. So the graph, we don't cross the intercept, the horizontal asymptote, sorry, it goes to negative infinity. Okay, keep in mind that we don't cross the axis right here. And we know so it's concave down from negative 3 to 6. And if you look at that, basically it from here to here, it goes to the origin. It is the maximum value, and it goes to here. And that's concave down. And from 6 plus infinity, it goes to concave up, but we do not We do not cross the x-axis, which is the intercept. Now again, that's a horribly drawn graph, but it's effective and it's something all I want to see on a test. So again, your extrema, inflection points, intercepts, and your asymptotes. And again, that's how you sketch a rational function.